there's our little splash screen, which gives you a little flavor of what this is about. So what we're going to be showing you tonight is actually the first element of this new program that we are creating. Ancient Origins of the Gulf is what we're going to be showing you tonight. The larger kind of module that sits inside of is the Delta Through Time. And so the Ancient Origins takes us from, we're going to time travel back 200 million years to the early Jurassic period, and then progress forward to about 10,000 years ago. And that gives, the context for the birth of the Gulf of Mexico and the early formation of the Gulf Coast and the early formation of the Mississippi Delta. And then the subsequent parts of this, which we're not going to share with you tonight, but this will be available for folks to explore, go into the birth of the last 6,000 years of the birth of the Bird's Foot Delta, and then exploring ecosystems of the Delta that have now flourished on this geologic foundation. And then the last piece is looking at kind of the social layer, people, problems. There have been some significant issues that have evolved from the history of our involvement with since people have been making significant changes to the systems in the Gulf. And then looking at possibilities. It's, there's big efforts at work to try and redress some of the issues there. So we'll start out. I'm going to play this video, The Ancient Origins. And as I say, Jackie was a key person in helping us to figure out how to frame this and, what is the key parts of the story. And then our graphic designer, illustrator, and animator, Lee Simmons, did the animation work that you'll see, which we're very excited about. And then we layered that into a video presentation. So this is about 4 minutes long. We'll play this, and then I'm going to turn it over to Jackie. So buckle your seatbelts. We're going back.
Let's time travel. Destination? The early Jurassic period. That's right, the days of the dinosaurs. As we fly back in time 200 million years, you can see the continents changing shape and positions as the tectonic plates that form Earth's surface are on the move. And we will arrive just in time to witness the birth of the Gulf of Mexico. In the early Jurassic, Africa was drifting eastward, saying goodbye to South America, which was moving towards the south. As the continents moved apart, ocean water entered the space they had occupied, and the Gulf of Mexico was born. The newborn Gulf was shallow, and its waters were warm. Those conditions, along with changes in sea level over the next 70 million years, resulted in extensive evaporation. The sun's warmth turned Gulf waters into water vapor, leaving behind huge salt deposits that covered large areas of land, creating landscapes that would have looked something like today's Bonneville Salt Flats near the Great Salt Lake in Utah. During the Cretaceous period, higher seas covered the Gulf region. For the next 70 million years, as aquatic plants and marine creatures lived and died, their remains accumulated on the sea floor. Coral reefs grew and gradually compressed into dense layers of limestone. The Gulf continued to expand and its waters deepened. As this happened, a different kind of limestone formed from the accumulation of microorganisms on the seafloor, a material widely used for sidewalk art and on school blackboards, chalk. After the Cretaceous period, sea levels dropped and the Mississippi River began flowing toward the Gulf. On its downhill journey across the continent, the river picked up and carried massive amounts of sand, silt, and clay to create a growing delta made of material from the far reaches of the North American continent. Today, tall buildings in New Orleans sit on top of this massive accumulation of Mississippi River sediment, and far below them the layers of chalk, limestone, and salt. The many layers of sand, silt, and clay are as much as 6 miles deep and form a foundation for today's Mississippi River Delta. Their unimaginable weight has produced some extraordinary effects. Under extreme pressure and with heat from Earth's core, long dead sea creatures and aquatic plants were gradually transformed into oil and natural gas. The tremendous weight and pressure also affected the deeply buried salt layer, which is less dense than the material above it. Behaving much like liquids do when placed under great pressure, in places, salt would rise upward in formations called salt domes. As the domes made their way toward the surface, fault lines formed. The heavier sediments above and around the domes slid downward. Oil and gas accumulated in pockets formed along the fault lines. These reservoirs of oil and gas are tapped today by wells located throughout the delta. Underground movements of salt still happen today. Sometimes they produce spectacular results, like suddenly appearing sinkholes big enough to swallow large trees. Many of the processes that gave birth to the Gulf and built the foundation for today's river delta are still at work. Ever more sand, silt, and clay, deposited by the Mississippi at its mouth, has been shaped and shaped again by powerful floods and storms, and by the relentless movement of the river's currents and twisting channels.
All right, and with that, I'm going to stop sharing my screen. Jacqueline, go ahead and take over. The rest of the presentation is yours.
Absolutely. Thank you, John. It was really exciting to work on this project with everybody before I jump in. As I've said before, this is a project I've rolled around in my head for about 10 years. So it's really exciting to watch this come together. It's like birthing a child in 4 minutes. It's very exciting. So tonight I'm going to talk about the main aspects that we're going to see, that we saw in the animation. This is a very abbreviated version of a much longer talk that I usually give. I usually talk with the Louisiana Master Naturalists for about 3 to 3.5 hours about this subject. I am not going to keep you all here that long. So we're just going to go through a quicker version of this, and we're not going to get into a lot of the complexities that I'm always tempted to get into. So we're going to go ahead and get started. And we're going to start here with just an overview of what we're going to take a look at. So as you saw, some of the main players, right, for rock types, we have our salt, we have our limestone, we have our chalk, and then of course, all of our soft sediments. And so we're going to really talk about how those came to be, why they're there, and why it's important today. But of course, as you saw in the animation, we're going to scoot all the way back to the breakup of Pangaea, because that's really where the Gulf of Mexico starts. And this is always fun for me as a geologist to kind of tie all of this together, this big thinking, and see how it all plays out. So we're going to take a look at the breakup, right, of Pangaea. We're going to take a look at the opening of the Gulf of Mexico and why all that salt is there. We're going to take a look at some limestone development, and then we have lots of river progradation that we're going to take a look at, and really the building of Louisiana, of our great state. So going all the way back, right, to the Jurassic, this is where we are tectonically. And it's really important to recognize that our plates obviously were not in the same position. That is a big player for climate and how these rock types are going to get deposited. So if you take a look right here in the upper left-hand side, you can see we've got Pangaea all together. And we're going to see here that as Pangaea starts to break apart, we're going to get some water, right? That's going to come in and eventually form the Atlantic Ocean and the Gulf of Mexico. Now, the formation of the Gulf of Mexico is actually a really complicated topic. So I am going to make it as simple as possible and kind of gloss over the geophysics. I know I have some students here on this talk and they don't want to hear any math. So I am just going to gloss over some of that part. But this is really important, right? Because if Pangaea hadn't broken up, obviously our world would look very different than it does today. So if we take a look at the opening of the Gulf of Mexico, as Pangaea started to break apart, right, we saw in the animation, Africa and South America and North America move away from each other, we get the opening of the Atlantic. The opening of the Atlantic is actually a fairly simple and straightforward topic that I love to talk about in my Geology 101 class because it's pretty straightforward. However, when we look at the Gulf of Mexico, it's a little bit of a different story. Of course, we have the opening here of the Gulf of Mexico tectonically, but we have some complexities in here. Those of you that may have taken a cruise out of New Orleans may have wound up in the Yucatan. Maybe you've gone to Cancun. Well, that area didn't originate right where it's at. It has moved over time. And here you can see on the left, it broke off of North America and it is rotated to where it is today. And that rotation actually facilitated the opening of the Gulf of Mexico. So this is a fairly complicated geophysics math problem. So if you love math and love calculus, this is definitely something you want to dive into. But as the Yucatan rotated, it helped open that basin. And we're also going to talk here in a little bit about the salt, which also kind of helps open the basin just a little bit. Now, when I talk about the basin, we have in our heads, right, what it looks like today. And you can see up here in the upper right-hand side, you've got your coastline, right? That's what we're used to looking at. However, back in the Jurassic, it didn't look that way. The original edge of the basin is here marked in red for you. So that was the actual edge. And you can see the actual edge is way up here, right north of Louisiana. So really that opening of the Gulf of Mexico, and we're eventually going to see the Mississippi River come down, is really what helps build this region. So it's important to recognize sea level, right? Sea level's role in this. And you see up here, this is called eustatic sea level changes. The word eustatic means worldwide, right? So this is not something that's happening right here in this local area. This is sea level around the world. And here we are in the beginning of the Mesozoic, and you can see sea level is fairly low. Things look a little different. You can't even see Louisiana on here, but you can see a little finger of the ocean kind of coming in here. And then as we move into the Jurassic, you see sea level gets a little bit higher in the continent. We call this an epicontinental sea. That's just a fancy word for meaning on the continent. And that's going to be important here in a second, because as we talk about these sea level changes, that's what's going to make the river move in the direction that it currently is in. But as Pangaea started to break up in the Jurassic, you can see here that we have this very early ocean, right, that's starting to form. And sometimes it's really hard to imagine what these things look like. So if we want to get a modern example of what this looked like, we can definitely take a look at the Red Sea. The Red Sea right here, just to give you a context, here we have Africa, right here we have Saudi Arabia. Saudi Arabia used to be attached to Africa. If you take a look at those coastlines, you can definitely see that those match up pretty well. But as Saudi Arabia broke apart, you get the invasion of a small seaway. Now, Saudi Arabia and Africa are still moving apart today, so that ocean's only going to get bigger. And so if you really want to get that good mental picture of maybe what the beginning of the Atlantic or the beginning of the Gulf of Mexico looked like, this is a great place to start. That's the cool thing about geology, is you can find examples everywhere. As I tell my students, geology is nothing more than Earth CSI. There's clues everywhere, right? And you just have to interpret it to figure out what it means. Now, as the Gulf of Mexico started to open, it wasn't this big gulf, right, that we have today. It was very narrow and skinny, just like we saw with the Red Sea. And the waters weren't incredibly deep. And that's just going to lead to a lot of evaporation. And when you have evaporation, you're going to have salt. Those two go hand in hand. So on the left here, right, what you're looking at is everything in purple is where we have salt deposition. Now, it's important to recognize that this salt forms the basement, right? Part of the basement of the Gulf of Mexico. I know in Louisiana, we don't have basements. I'm from the north, so I know what a basement is, right? It's the bottom level of the house. So the salt here is the bottom level of the house, right? And that's going to be really important here in a few moments when we talk about the movement of that salt. Now, as water started to deepen, right, we're going to, on top of that salt, we're going to get limestone. And that's going to be another really, really important player here. So that limestone here is deposited in this area that's blue. If we're taking a look here in the Cretaceous, everywhere in blue had all of that limestone. Now, limestone is important because, again, if we're talking about clues, right, trying to figure this out, limestone tells us exactly where we are and what environment we're in. Limestone only gets deposited in coral reef environments. So this tells me, right, that this area of Louisiana back in the Cretaceous time period was definitely very different than it is today. right? So we had nice coral reef deposits. It tells us it was warm tropical water, and we have all of that limestone deposition. So now we're starting to put weight on top of that salt. And as you saw in the video, when we get enough weight on top of there, that salt is going to start to move. And so having this nice solid rock on top of there is definitely a key component to helping that salt move. Now, when we get to the Cretaceous time period, it's important to note what sea level looked like. So on the left, you can see we have this finger of the epicontinental seaway coming all the way down, not quite connecting up with the Gulf region, but it's pretty extensive in North America. So when you have a seaway on the continent, most of your rivers are going to drain that way, right? They're going to drain towards that seaway. And you can see that up here, right, in this top picture. So everywhere in green, that watershed went straight to the seaway. Well, today, we know that we don't have an epicontinental seaway, right? I'm not going to go to Nebraska and go swimming in the ocean. I'd have to go way back in time to do that. So we know that that seaway closes, right? Sea level starts to drop as we start to get colder and the climate changes, and the seaway moves, right? It disappears. Now, when that seaway disappears, that means your rivers are going to have to change where they're flowing to, right? And so what we start to see is this big shift where rivers now are going to start, as you can see in this area, come straight for us. And that's really important. That's the first step in the Mississippi River working its way down here. Now, just as a cool side note, for those of you that like random facts, when the Gulf of Mexico, and I see one of my students there smiling because as they already know, I like to spout lots of random facts and keep it interesting. When Pangaea started to break apart, a little bit of Africa got left behind on North America. So if you've ever been to Florida or a little bit of Georgia here, you've actually been on African crust. So that part's really cool. I've tried to convince my 15-year-old that he's been to Africa, but he just doesn't buy it. All right. So as we move into the Cretaceous, all of that water is now starting to move down this way. And as those rivers start to move down, we're going to get some very early delta deposits. And so in the late Cretaceous, right, as that seaway shift started to occur, we're going to get a very early sand deposit, a sand lens down here, the Tuscaloosa Delta. And you can see this is a pretty wide area with lots of little fingers of deltas getting deposited. And for those of you that like minerals, there you go. There's your close-up view of what those sand grains look like. Now, as the Gulf of Mexico continued to open, that water definitely deepened, right? And as that water deepened, we're going to start to see different kinds of deposits. And so in some regions, we get the deposit of chalk. Now, chalk is really neat because, again, like limestone, it tells us exactly where we are environmentally. Chalk only gets really deposited in deep, deep water. And it's formed from the compression of these microorganisms down here on the left. These are called coccolithophores. And when you get a mass death layer of these coccolithophores, they compress and turn into chalk. Now you might ask, well, what causes mass death layers of these coccolithophores? They're very sensitive. So you can have a slight pH change in the water or a slight salinity change, and you're going to get a mass death layer of these guys. But it always amazes me when you start to look at these giant chalk layers and realize it's made up of these tiny, tiny microorganisms. It kind of puts it into perspective. And as we move out of the Cretaceous, our climate is changing. We know that in our current time period, I know it doesn't feel like it, but we're still in the ice ages, right? For now, hopefully it stays that way. We have ice caps, right? And as long as we have glaciers, we're in the ice ages. And this is where we start to head into it. Right at the beginning here of this time period, into the Paleocene and Eocene you see here, we're going to get one major push of heat, right? The climate's going to change, it's going to warm, and then we kind of dive off the diving board into some very cold climate. So what we're looking at is called the Paleocene-Eocene thermal maximum And we can measure that by looking at oxygen isotopes in core samples. And that tells us the ratio of oxygen isotope 18 versus 16 actually tells us what the temperature was. And it's really cool science, in my opinion. But at this point in time, as you can see, the seaway is very high, right? If you look, you can see just the top of Louisiana here. And so as we move into the Eocene, you can see it fills up even more, and you get this finger of the seaway coming all the way up almost to the tip of Illinois. And that's the extent of it that's going to happen. And then, like I said, we're going to dive off now into colder climates. Now you might ask, why do we have this thermal maximum? Boy, if you love to see geologists argue, this is one topic that you definitely want to mention in a group of paleontologists or geologists, because there's a lot of controversy around this one. But we do know that there was a lot of carbon that was input into the environment at this point in time. We know we had lots of volcanism going on. This is about the time when the San Andreas Fault was starting to become active. And we have lots of volcanoes, and that may have helped facilitate that change in temperature. But it's always interesting to me when we take a look at what's going on in today's environment and compare it to what we see in the rock record. At this point in time, we have ocean acidification going on, which maybe that's something you've heard of today, right? Because this is how we're losing some of our coral reefs. And when we start to see that ocean acidification, that's telling us we have a very high carbon dioxide content that's being dissolved into the water. Now, as we move into these colder climates, we're going to start to see the Mississippi River really work its way down here. And we form what's called the Mississippi River Embayment. And if you take a look right here on the big colorful map, I love this map, you can see this is basically like a river valley, if you want to think of it like that, an incised river valley. Those of you that have been to Mobile, Alabama, that's an incised river valley. If you could take a look, it's really small compared to this one. It's right there, right? There's Mobile incised river valley. This is basically a very large version of that, much, much larger. And what's really cool about this picture, and I'm going to kind of show you again here at the end, is each one of these colors stands for a different time period. And what we're basically looking at is the lowering of sea level. So with every color that you see, this is the new beach. So originally, the beach is right where that gray touches the white, and then sea level drops. Right? And now we're down into the blue. Sea level drops again, and we're down into the light blue, right? And so on and so forth. So you can really see, right, how sea level affects that river movement, right? Coming downwards and depositing. So basically this incised river valley fills up with delta sediment, and it continues to work its way down. Now on the right over here, I put in this little picture because it's a really interesting conversation on how and why the Mississippi River Embayment formed the way it did. And one thought, and there's many thoughts on this, again, there's lots of topics where we have lots of friendly arguments, right, between geologists. But if we take a look, this is actually what you're seeing in red here is an old rift zone. So North America, back about 3 billion years ago, 2.5 to 3 billion years ago, tried to break apart into two pieces. It did not break apart all the way, but it didn't slam back together. So we kind of have this loose area in here. This is called the Mid-Continental Rift. And we can actually still get small earthquakes, okay, in this region, just because it's a broken piece. Now, if you take a look at this area in red, I want you to notice that it's kind of similar in shape to what you see here. So it's thought that the topography of the land due to that old rift valley may have dictated why we see the embayment take the shape it does. But I just want to throw that out there because I think it's really neat how you can get incredibly old geology that still affects things today. That's kind of my favorite. Although, as my students can attest, every single thing I talk about, I say is my favorite. It just is what it is. Now, as the river starts prograding means, right, marching out to the ocean, we're going to get lots of sand and silt and clay deposits, right, as it moves down. And one of the first there is the Wilcox Formation. This is a very large delta deposit as the river starts to move downwards. And this is important because the weight of the Wilcox Formation on top of those layers below it is what started the movement of the salt. So we have all these rocks pressing down on the salt. Now, salt, as you saw in the animation, is lightweight, right? It kind of acts like water. If you push down on it, it's gonna move upwards. So as the weight of those rocks are pushing down on the salt, that salt's gonna start moving up. And I really love that part of the animation when you can see the salt dome moving upwards. And as it moves up, it starts to tip the layers around it. And as those layers are tipped and maybe broken in some spots, all of the petroleum is gonna accumulate on those upthrown blocks. And that's what makes it very easy for us, well, easy, we'll put that in quotes, easy-ish, to get the petroleum out of the ground because it's in that small concentrated pocket. So without these salt domes, it would be incredibly difficult to extract the petroleum. Now, if you want to know what it really looks like, what a salt dome looks like in seismic, you can take a look here on the left. Those of you that may not know what seismic is, as I tell my students, very easy. It's basically like an ultrasound for the earth, right? You can take a look and see the layers. And so what you're looking at here is this salt dome that has pushed upwards, and you can see how those rocks around it are tipped, right, as it moved up. Now, just as a side note here, during this time, we have some very large events that are occurring. The geology of the Gulf Basin is not nearly as straightforward as I'm making it sound. I'm giving you the highlights. There's a lot of really cool, complicated things that occur. And one major thing is called the Lobo megaslide. And it actually didn't occur over here where we are, but it occurred over here in Texas, this whole area that's kind of in this light tannish color. So as these rivers are moving down, they're depositing nice soft sediment, and you may have harder rocks further north. Well, hard rocks and soft rocks don't stick together very well. And so basically what happens here is all of this soft sediment that was just deposited by these rivers flowing down in Texas basically calved off like a glacier breaking apart. And so this whole area, and I want you to kind of envision what this would have looked like, this whole area in tan slid off of Texas out into the Gulf of Mexico. I can't imagine what the waves would have looked like, right, from something like that. It's pretty incredible. And now I bring that up because that's not the only mega slide that we see. Like I said, hard rock and soft rock don't stick together very well. And we have a very similar problem here, right, in Louisiana. There are lots of faults that cross the delta due to different subsidence rates. But if we take a look up here, one of our bigger overarching faults is the Baton Rouge fault zone. And we basically have the exact same problem that the Lobo megaslide was. We've got harder rock to the north, softer rock down here to the southeast, and they're not sticking very well together. And so basically what's happening here in very, very slow motion, I mean like 5 millimeters a year, the whole southeastern region of Louisiana is slowly breaking off and falling off into the sea. Isn't that fun? So I tell my students, geology is really just the 1,001 ways the earth is going to kill you. That's just how it is. So this whole area, eventually, right, we're going to see some movement. And if you really pay attention, you can see some of these faults throughout the delta. If you drive across the causeway, right, one of the largest bridges that we have, there's a very slight jog around mile 2021. And that's because a fault line is right there below the causeway. It's very slight. You really have to pay attention. Now, as we move forward, the river is just going to continue to prograde. And I'm not going to talk about every single deposit, but just know as these deltas are moving, you're going to get delta on top of delta on top of delta. And so when we look at the deltas down here, and this is the part that's always fascinated me, when we look at the formation, we generally tend to stick to the last 10,000, 6,000 years. But really what's happening, or what has happened in the recent past, is exactly what happened at this point in time throughout all of the Cenozoic. And so what we see here, right, is just these deltas moving downwards. So for those of you that may not know how these deltas form, basically what happens is the Mississippi River is moving real quick and it has lots of sediment, an amazing amount of sediment in there. And when it hits the Gulf of Mexico, it's like hitting a brick wall. That Mississippi River slows down and it can't carry that sediment, and that sediment drops out. And you get a pile, right? And that's what we call the delta. Now that pile is going to continue to build and build and build, but that river is not going to want to keep plowing through that delta. That's not very energetically efficient. So it's going to move around that delta and deposit a new one. And when that gets too big, it's going to continue to move. So the river doesn't go in one place, right? It's going to move back and forth. And that's quite literally what we're seeing here. So let me flip through some of these delta formations. So we start here, and believe it or not, guys, we have some fossils in Louisiana. That makes me very excited. They're very hard to find, beyond rare, but we do have some fossils from these time periods. So if you really like a good scavenger hunt, and I mean a really good scavenger hunt, there you go. But again, like I said, we just have this progradation of those deltas as they move further and further down. Now, if we take a look as we move into more recent time periods, what you see here is, I want you to notice, and you may have noticed it in the animation, that the land built further outwards than where it is today, right? Because sea levels were much lower as those glaciers were very large and were in the glacial time periods. I really kind of wish we were still like that, because then we wouldn't have the coastal erosion problems that we have today. That would be fantastic. But unfortunately, that's not what we're dealing with today. So there we are, even more delta formation. All right. See, can you guys see how this talk goes 3 hours if I really go through it? But this is a geologic map of North America, and it's really the only textbook you need for geology. Literally everything you need is right here. But if you take a look at this geologic map, I want you to notice you can see that Mississippi River embayment, right? And that Mississippi River embayment is very obvious, and you can see that progradation of the delta and the lowering of sea level right through geologic time. Now, as we move forward, we know those glaciers get really large, and we can see evidence of glaciation all the way down here in Louisiana, believe it or not. If you've ever been to Tunica Hills, which is one of my favorite places to hike, you can also see some of the only waterfalls we have in Louisiana. Tunica Hills is what we call a loess deposit. So what happened here is we have this very large glacier that's moving down right across North America. I went to school at the University of Kansas, and in Kansas, even though it's flat, right where I went to school, there's these big rolling hills. And when I say big, they're big. And it's because that's where the glaciers came all the way down to. Now, glaciers are like giant desert environments. The wind can really whip across those glaciers. They're very dry. And glaciers are not just pristine, beautiful ice. They have a lot of sediment loaded in there. So that sediment can get blown off of those sediments or blown out of those sediments. And it gets incorporated into the Mississippi River and gets brought down here to get deposited. So we have this really large deposit, like I said, of those glacial sediments. And then, of course, I'm going to kind of end our story right about here, because I know our next meeting of our webinar is going to kind of take over from this spot. But this is where we tend to start thinking of, right, Louisiana. But I hope that you guys recognize that everything before it is what really helped lead that river down here and exactly where it's at and help funnel it. And so when we take a look at modern delta formations, we know that those deltas literally formed in the exact same way that all of those deltas preceding it did, just more modern. And I'm going to leave you with probably my favorite picture. And this is where I wish we were back in the classroom and there was no COVID, because I have this wall sized on my classroom and it's beautiful. But as we move right into those glacial cycles, these watersheds start really becoming active. And here I hope it's very easy for you to pick out the Mississippi River watershed. It's in pink, if you didn't figure it out, right? It's the 6th largest river in the world. And of course it drains most everything right from the Rockies to the Appalachians. And so without this dynamic system, we wouldn't be here. So the story of the Mississippi River is a lot more complicated than just the last 10,000 years. And if we didn't have all of that preceding it, we wouldn't be here. And here is my obligatory, I did all of my research. And so there we go. Thank you guys for listening to me. I appreciate it. And let me give the reins back to Tracy or John.
Well, thank you very much. A round of applause is be given at this point. Thank you very much for that. I always learn more and more as I listen to you, and thank you for sharing some of the other links. Chris, those are some pretty interesting things that you had thrown out there. So that was kind of neat. That's what's fun about an actual presentation. You can kind of start looking at a few other things as and have if you're into multitasking. We did get a few questions. And there was one by Emily about, and I think this was during one of the times when there was the continental ocean or continental sea. How can the water flow uphill? Was there isostatic adjustments when the water left? I believe that's in reference to that.
Gotcha.
That time slide.
Yeah, Chris actually answered that pretty well in the discussion there. We at that time, when we started to see the rivers shift, or where they're flowing into, at that same time is when we're having mountain building in the West. So we have all those mountains that are forming, and in the Cretaceous we have a couple of orogenies, and that's also kind of helping move the water as well. Of course, there's always going to be isostatic adjustments. Absolutely, especially as those mountains are forming, right? As they form and get larger. Those of you that don't know what isostasy is, the crust basically floats, right? The lithosphere floats on top of the asthenosphere. And much like a boat on the river, when you load it with weight, it sinks down. And when you take the weight off, right, it rises up. The continental crust does the exact same thing. So as that area was getting crunched, right, to form some mountains, it's going to help kind of move that water in another direction. So hopefully that answered it.
Another question was, how does the Mississippi Delta compare to the Nile or the Amazon? You mentioned that was the sixth largest. Are there what are the similar? Well, I guess how do they compare?
Well, the interesting part as far as deltas go is deltas pretty much form in a very similar way all around the world. It's, if you want a $5 word that unfortunately doesn't fit on a Scrabble board, it's called uniformitarianism. Basically, the present is the key to the past, right? And so when we look in the fossil record or look in the rock record and see how these deltas formed, we look at the Mississippi River and see how it's moved and prograded downwards. We can really apply that to most rivers that we see. They're going to operate on the same way, just maybe on a bigger scale, right? If we're talking about the Amazon or the Nile, or a much smaller scale if we're talking about something like, say, the Pearl River. But they all pretty much operate the same way.
Here is another question. Does the upper Mississippi River follow the mid-continental rift? And I'll let you answer that. I have a little follow-up question after that myself. So that is a question.
Yeah, that is a great question, actually. So the mid-continental rift is definitely a point of weakness. As I mentioned, we can still get earthquakes, right, that occur there. So I don't have a good, well, I guess we can kind of take a look. Let's see, Tracy, if you go back, or whomever is sharing, if you go back a couple of slides to my super, yeah, one more, there you go. Go forward one, perfect. So if we take a look at the rivers here, in comparison to, I'm pulling this up on my end, to that, we're going to be up here kind of on the edge of this green and pink up here. And if you take a look, it's actually pretty hard to distinguish where that mid-continental rift is. So that mid-continental rift is actually happening really deep. It's been buried, those rocks that were broken, and you've got lots of sediment deposited on top. So it has kind of buried that weak zone. However, if that weak zone was up at the surface, absolutely, water would definitely follow it. Like you said in that question, water always follows that path of least resistance.
one thing I would say is I believe that Lake Superior is a remnant of that, very
Yes.
much is my understanding. And
Yes.
I love that that you talked about the shapes that parented that. I never had thought about that or seen that before. But I believe that the Lake Superior is part of that rift system.
Yes, it absolutely is. It's really cool. Like I said, it's one of my favorite things to realize how ancient geology still affects us today. It's always kind of amazing to me.
Well, here's one. How was Florida formed?
Good question. So Florida was actually attached to Africa. And so what happened is when North America and Africa collided, right, we formed the mountains. Now the Appalachians didn't just form that way. It's much more complex than that. But they were the last mountain building event of the Appalachians. And then those two continents stuck together for a while. And then we have plate tectonic forces that's going to break them apart. When it breaks apart, plate boundaries don't care about dividing things equally, right? It's not going to say, well, here's the old boundary. Africa, you go that way. North America, you go that way. It's going to break on the thinner side. Mountains are really big and thick, so the continent's not going to crack through there. And it ended up cracking on the African side. So that little sliver of Africa, right, Florida and little bits of Georgia there is what got left behind. And so the basement rock there of Florida is Africa. And then you're going to just get your normal deposits on top. Florida actually has a lot of carbonates. One of the most extensive cave systems in the world is actually in Florida, but it's still flooded, so you can't walk through them. So it's actually pretty interesting and leads you to all of the understanding about all the large sinkholes that occur in Florida. And clearly you guys see that I can talk about these things for a long time, but it's really quite interesting. So Florida comes from Africa.
When we were making this, you also gave us information about the Yucatan. You might want to about the rotation of that, and you were very clear that that is something we should try to visualize because it's not always done. But maybe you want to talk about that aspect as well. It sounds like a similar connection in the plates.
Yeah, absolutely. It's in general, plates kind of leave themselves, leave little bits of themselves all over the place, kind of like glitter, right? As things break apart, you're going to get little bits and pieces stuck everywhere. And the Yucatan is no exception. So as these continents were breaking apart, that little sliver of over there that was in Texas broke off and eventually it became the Yucatan. Now, when it broke off, it rotated, and that rotation of it is what helped open the Gulf. Without that movement, without that rotation, the Gulf of Mexico probably wouldn't look the way it does today. So that was a really major player. And it's important that we highlighted it because it's really hard to depict this tiny little sliver of land moving and rotating inside of the Gulf of Mexico. Like I said, the Gulf of Mexico's geologic history is really complex. That was one really important part I wanted to be sure we included because unfortunately a lot of animations just skip over it. So I'm really, really happy that we were able to include that part in the animation.
Here is one from Britta, our dear friend over in Stillwater. She is wondering if the historical deltas correspond to glacial events.
Well, you will definitely see glaciers play a huge part just in rivers in general. When glaciation is really high, so meaning large glaciers, that's when we really start to see rivers become active. Because of course you're going to have, glacial melting in the, in the summers and then freezing in the winters. And so we really see more delta formations and more land building in these glacial time periods when those rivers can be active. So yeah, you can absolutely make those correlations to some of these deltas that have formed in that progradation to those glaciation events.
Excellent. We know that the oil industry is an important part of the economy of the Gulf and Louisiana. Are salt domes part of petroleum deposits everywhere oil is found?
Not everywhere. In other places, it's different kinds of deposits. Usually, in general, wherever you're going to find petroleum, that petroleum is going to be in a rock that has lots of, say, airspace, right? Porous space in between it, like sand. And usually it's going to be capped by something really, really hard that's not porous, that doesn't allow the oil to go through. So in other areas like the Williston Basin, which is up in North Dakota, and Montana, that whole region, that's actually where I do a lot of my field work. It does not look like the Gulf of Mexico at all. There's no salt domes there. So down here, it's just that oil and gas would have been there anyway. It just would have been really, really hard to extract it from a sand. I don't want to think about taking liquid out of a sand or gas out of a sand. That sounds miserable. So the salt dome just helped facilitate making that a lot easier to get it out. But no, salt domes are not needed essentially always to get that oil and gas out. So hopefully that kind of answered that. That was a great question.
All right. Well, with that, what I would like to do is to turn this to John for 1 second to give an overarching framework of where this materials can be found, because the geology is but one part of the river that we're looking at. As I said, it's kind of a big picture looking at one river thinking. So John, we have a few minutes left, about, not many, because we do want to honor our 7 o'clock time. But if you want to just, if you could show the waters to the sea, how you might find this and how an educator, teacher might use this, access this for their classroom, would be kind of fun.
Okay, I will happy to do that. So this Waters to the Sea program is something that's sort of our legacy watershed and environmental education initiative. It's been going on for more than 25 years now, so it's evolved over time. What we're looking at right here is the homepage for our Mississippi River Adventure Waters to the Sea program, and we've done versions of the Waters to the Sea for rivers in Texas, other rivers in southeastern United States. We have a version, a couple of versions in the Hawaiian Islands. So we're taking this concept and applying it many places. But the Mississippi is where we have kind of the richest content. There's probably, you could think of this as sort of a compendium of probably 6 or 7 hours worth of content that really tells the story of how humans, social, cultural systems have interacted with natural systems throughout history along the length of the river. So this is the main menu page. Real briefly, I'll jump to what we call the river journey. And so this whole program has a very strong map-based component to it. This map that's opened up now has the river corridor with green hotspots. So you can think of this as a storytelling tool that is place-based. And so one of the ways you can find content is by zooming in. If you zoom in 3 levels, you'll start to see all the tributaries of the Mississippi, and go in 1 more level, you'll see the county boundaries. And every place you see a green dot, there's a story there, and you can hover over that to find out what the story is. So that's one way you can find content. We have a lot of content down in the Delta. And then there's also a menu on the left. You can scroll along this and find content that way as well. And then there you can see the tabs across the top break all of these stories down into subject matter topical areas. So earth science, life science, social science. So when you click any of these tabs, you're going to see a subset of all of those place-based stories that were on the River Journey tab. So that's one way content can be found. Again, there's tons of stuff in here. Videos, interactive panoramas, simulations. I'm clicking the media index, and that quickly will show you that's another way of finding things. So we have these interactive modules that are more fully kind of using multimedia in an interactive format. We have 360 landscape panoramas at numerous locations along the river, and then many, many videos as well, as you can see. And then we have also, very important for educators, a teacher resources area. And here we have a scavenger hunt, which is a great way to begin to explore this resource and find out what's there. Plus we have a matrix that lists all of the media elements in waters to the sea and how they correlate with different standards and the NGSS standards, plus a whole series of lesson plans and complementary activities that you can do in the classroom. So everything we've looked at today, this new visualization of the ancient origins of the Gulf and the other parts of our delta through time that will include the birth of the Bird's Foot Delta and ecosystems of the delta, those are going to be added in here. So we're constantly updating and adding content to this. So that's a quick overview, lots to see here, and we'll make sure everybody gets the link to this. You're welcome to, this is all free. We have an hour-long PBS documentary we co-produced with WYES New Orleans, and we have segments of that playing through this as well. So lots of rich resources.
All right, thank you, John. Let's see, I wanted to do one shout out that I did not quite get to begin with, but I wanted to thank Ami for following us and our friends at Loyola. That we have had some wonderful times working with those folks as well. So that's the thing when you have a lot of good partners, you got to make sure that you do try to say hi to everybody and make things sure you recognize your friends. With that, John, can you play us the On Waters to the Sea before we go? Mark Twain giving us a little bit of overview, because I see that we have one of our guests on, Don Shelby, who has been a dear friend of ours over the years, and you might recognize who this Mark Twain character is. But that will take us out on this, and we still have about 90 seconds, so I think we'll be okay.
All right, happy to do that. Hey, Don, so glad you could be with us. Thank you for joining us. So I'm going to zoom down into the video section here. We have two videos featuring Don as Mark Twain. And let's see if I can quickly put my finger on them. One of them, we'll do the, it's a very short one. Hang on one sec. I know I'm looking at it. Here we go, Life of the Mississippi with Mark Twain.
Great Mississippi, the majestic, the magnificent Mississippi, rolling its mile-wide tide along, shining in the sun. The Face of the Water in time became a wonderful book. A book that was a dead language to the uneducated passenger, but which told me its mind without reserve, delivering its most cherished secrets clearly, as if it had uttered them with a voice. It was not a book to be read once and thrown aside. It had a new story to tell every day. Throughout the long 1,200 miles, there was never a page that was devoid of interest. Never one you could leave unread without a loss. Never one you would want to skip in order to find higher enjoyment in some other thing.
Well, that's a nice way to end on this snowy, cool evening up in Minnesota. Thank you all. We'll probably stay around and just chat a little bit afterwards, just having some fun. But thank you all for joining us. We'll be back in 2 weeks, or excuse me, in about 3 weeks, and talking a bit more about some Gulf issues. And we really appreciate everyone taking the time to explore and learn about the river. One river thinking is important. I know a lot of you folks are from Louisiana, and this is probably a bit old news, but for some of us in the northern part of the country, I know people are always excited to learn about another part of the world, and the Louisiana Delta is a special and magnificent spot. So with that, it's an official goodbye and thank you. Thank you, Jacqueline. Thank you, John. Take care.